Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. We thank you for your many mercies to us, Lord. Thank you that you're a good God and that you love us whether or not we love you. We thank you, Lord, for your grace each and every day for us, Lord. Pray with us today. Help us to, again, Lord, glorify you what we do. In your my prayer, Lord Jesus. Amen. Okay, so are there any questions about integration, homework, anything? So, of course, yesterday, some of the examples we did were pretty hard. But, the one we did at the start of class wasn't too bad, right? And those are nice examples. You should work the homework and try to come to an understanding of it for yourself. We're now in section 8.7, which is on numerical integration. So, so why do we need to talk about numerical integration? Well, you can't integrate everything is basically the thing. For example, you can't find an antiderivative of everything. There's a theorem of calculus that says that the integral from a to b of f of x dx exists. It's a number, provided that the function satisfies some relatively benign requirements. Continuity, for example, is enough. But even that's too greedy. You can still have the function's integral exists, definite integral exists, even if the function is just piecewise continuous. You could even be missing the definition of the function at a bunch of points, and it still would have a well-defined integral. So you might wonder what I mean when I say that the integral doesn't exist. What I'm really talking about are those functions where we can't find a nice formula for the antiderivative. So there's some important examples like that. For example, this one. If I want to know the antiderivative of this is not an elementary function. What's an elementary function? Well, basically it's some sort of sum, product, difference, etc., of things that we have names for. Sine, cosine, exponential, so forth, these sorts of things. There's a more technical definition, but it can be shown, I would not do that in here, ever, because it would be inappropriate, and I don't know how, that this does not have an elementary antiderivative. And yet this matters, right? What is this? What's the significance of this? If I integrate, what's this thing look like? So what would the significance of this area be for this thing? This isn't quite right. I'm missing like a k. There's some normalization constant I'm missing, but this is the so-called bell curve, right? And so that has the significance of being the probability of a certain event happening, right? So this is the sort of integral you'd like to know how to do, and yet we can't. Not with the fundamental theorem of calculus part 2, right? Because you can't find this thing, right? This is unavailable. Can you guys think of any other functions that are like this? How about this? Integral of I don't know, I think sine of x squared you can't do. In fact, most formulas you can write down, you can't integrate. The examples we worked so far are precious and rare. So that means we need some other method to calculate definite integrals, and that brings us to the basic methods here. So the integral from a to b of f of x dx can be approximated by a few different rules. You can use the left endpoint rule, you can use the right endpoint rule, you can use the midpoint rule, you can use the trapezoid rule, you can use Simpson's rule. All right? So in order to explain these, I first need to set up a little bit of nomenclature, a name Colin, if you will. So let's draw a picture. Here's A, here's B, and we have to partition the set between A and B into a bunch of subintervals. For the sake of not going nuts, we take equal width subintervals. So like here's A, here's x naught, x1, and we'll say B is equal to xn, right? So over here is xn minus 1, xn minus 2, et cetera, all right? Now, I can come up with some formulas here. So like the typical distance here, you might call delta x. Delta x would be equal to b minus a over n. And what's the formula for the ith partition point? Try it out. If you put I equals to 0, we get what? A. Put I equal to 1, you get a plus delta x. Oh, I'm an idiot. A is x naught. I'm an idiot. Look at this. Look at this. You guys don't believe it. I mean, come on. Good grief. No. Sad. 1, 2, 0. Okay, there we go. Nothing terribly profound going on here. So the left endpoint rule. Can we draw a picture of that? I'll draw it in red for a second, just to make my picture cluttered. I'm going to regret doing this. Oh well, it's done. So if you add the areas of these red boxes, right, that describes what's called the left endpoint rule. Left endpoint rule means you just define the approximating region by the left endpoint. What's the formula for Ln? Use a summation. I equals, however you want to do it. I'll say I equals 0 to n minus 1. And we do f of x sub I delta x. So like the area of this first, this guy right here, what's this area? That would be f of x naught times delta x. That's that area, right? I hope you guys saw this in Calc 1 as well, right? So we're in a review. Kind of a shocking transition, right? We're doing the Weierstrass substitution, and all of a sudden I'm talking about areas of boxes. It's kind of a, it's like, I don't know, there's some wide gulf between those topics, isn't there? Let's see here. So you had f of x naught, but you can factor the delta x out, right? So all you really have to do is calculate the sum of the values of the function like that, right? So there's like, this is a pretty slick formula for L sub n. How about R sub n? The right endpoint rule, you just do sum I equals 1 to n of f of xi delta x, which of course you could rewrite this as f of x1, f of xn, factor alpha delta x. There's also a midpoint rule, right? So the midpoint rule is this. You take the sum, I equals 1 to n, of f of x sub I bar delta x, where what? How do we define x bar I? That's the midpoint. How do you get the midpoint of each one of these like little subintervals? I've got 100 and 120. What's the average? Add them together, divide by 2, right? So we do xi minus 1 plus xi divided by 2. Going back to my picture again, and erasing the evidence of the left endpoint rule, if possible. Let me use my finger. I'll regret this later. Gets into cracks of your finger, you know. I'm gonna get marker cancer someday. Let's see here. Don't laugh about that, monsters. Let's see here. Bad people. Don't laugh about your cancer. Oh man, I wanted a green marker. Oh, look at this. I got all these markers, but not a green one anymore. Fine, I'll do it in red. So the midpoint is just what it sounds like, right? So that one would be like something like this. For here, would be something like that, right? Over here. So you can kind of even visualize, for my silly example, midpoint is going to be a better approximation, right, for finite n. I think it's more likely that it's close to the truth, right? Yep.
What's the bar over xi?
The average. It's the average of the ith interval. Okay, so these, it's possible you've seen these in Calculus 1, right? Okay, so what's interesting and new, perhaps, about this section is he actually gives us an error estimate for some of these. Let's see here. Here's the error estimate in the trapezoid rule, Simpson's rule. Oh, man. Apparently, he doesn't think this one's important enough to give us an error estimate for, so I'm just going to move on. Trapezoid rule, then. For trapezoid rule, Tn. Let's see here. Draw a picture. Give you a picture, kind of a sense of what's going on here. So the trapezoid rule is just kind of what it sounds like. I'll just draw it for like four regions. So here's A, here's B. And so what the trapezoid rule says is it says replace the thing you're looking at with a bunch of trapezoids. So that's like this. It's basically connect the dots, right? Do. Very relaxing, actually. Let's see here. And so this area is going to be what I would call T4. Now, what's the area, for example, of this one? You do f of a, right, plus f of a plus delta x. You divide it by 2, right? That gives you the midpoint. That gives you the average of these two values, right? I don't know if you know this or not, but this times delta x will give me the area of that, right? That's the area of the trapezoid. You take the average of the sides and multiply by the yeah. I mean, if you don't believe me, you can imagine, a green marker. You can imagine that it would be the average, right? And if you think about it, the area of the green rectangle is the same as the area of the trapezoid, right? Because like the excess above is exactly what's missing below. If you can imagine cutting this piece of the board out, flipping it over, and then putting it over here, that would be that green rectangle, right? So that's why this is the area of the trapezoid. So if you take the area of each one of these trapezoids, right, and you add them together, the formula that you get is as follows. Tn is equal to, and this is not something I remember. I mean, I could remember it. I knew it when I took this class, for example. Man, where'd you go? Why is this book so heavy? Let's see here. You're like, tell me about it. You know, I'm doing this all wrong. All right. What? This book is cheap. What's your problem? It was only $370 at the bookstore. I don't know what your problem is. Come on, it's pennies. Let's see here. Trapezoid rule. So f of x naught. Here, I'll my newfound energy not holding the book. I'll even derive it for you. Don't get used to it. I'm not going to derive Simpson's rule, so don't get used to this. Behave. So the cool thing here, right, and you can see it, is that there's like all I've done, right, this is the area of the first trapezoid, area of the second trapezoid, area of the nth trapezoid, right? So you just add them together. But you notice there's some commonality, isn't there? So you got, what usually people do is they factor out the 2. So we do b minus a over 2n, all right? And then, oh, I'm sorry, I lost my, my delta x over here, didn't I? Oh, wait a minute, what is that? It's already there, right? That's the delta x, for start. So b minus a over 2n, and notice I've got 2 of these guys, right? And I got 2 of these guys too, and I got 2 of these guys too, but these are on their lonesome, right? So we have f of x naught plus 2 times f of x1 plus 2 times f of x2, 2 times f of xn minus 1 plus f of xn. And there's your handy-dandy formula.
Could you just put 1/2 of delta x?
Yeah, you could. Yeah. That's the trapezoid rule. Let me suffer through this for something interesting for a second here. Let's try to do the trapezoid rule for the Gaussian function. So let's do Tn for f of x equals to e to the, I'm going to need your help with this, guys, e to the minus x squared. For the integral, let's do the integral from 0 to 0 to 2, all right, of e to the minus x squared dx with, and let's not make our life too difficult. By the way, I got to be careful here. No, we're okay. We're okay. Okay. Let's do it for n equals to 4, okay? So what's my n equals to 4? What's that mean for my x naught? We've got x naught equals to 0, right? What's x1 equal to? 0.5, right? x2, or 1/2, very good. x2 is 1, x3 is what? 1.5, x4, 2. So I need for you guys to calculate for me what is, I'll tell you what, I'll do f of 0. I got that one. But what I need from you guys is f of 0.5. So that's f of e to the minus 0.5 quantity squared, you know? Excuse me, to be more careful, it's e to the, let's say it's, I don't know how you want it, exponential of minus 0.5 quantity squared. I mean, the minus is not part of the square, to be clear. I'll do f of 1, since I'm such a nice guy. That's 1 over e. Although I would like to know what's the value of 1 over 2.71 approximately. F of 1.5 I need from you guys. That's the exponential of minus 1.5 squared, or if you want the exponential of 2.25 minus 2.25. And finally I need f of 2, exponential of minus 4. What's that equal to approximately? I would like these in up to 2 decimal places just for the sake of discussion. So you guys tell me what they are. Anybody have this one for me? E to the minus, this first one, f of 0.5. What do we got?
0.778.
I'm sorry, 0. What? 7.8. Sure. All right. 1 over e. What's 1 over e? 0.37. Sounds right. What's the next one? Exponential of minus 1.5 squared. What's f of 1.5? 0.11? And what's f of 2? 0.02? All right, hopefully I've got enough decimals here. All right, so let's calculate what's the trapezoid rule then. T4 is equal to, and let's see here, what's my delta x? 4 minus 0 over, excuse me, 2 minus 0 over 4, right? You guys already knew that's 0.5, right? Okay, so I've got 0.5 divided by n, 2n actually, right? Excuse me, divided by, idiot. This is delta x over 2, right? So I've got 0.5 divided by 2 times what? 1 plus 2 times 0.78 plus 2 times 0.37 plus 2 times 0.11 plus 0.02, close parentheses. So you guys tell me what that is. T4 is approximately what? Can you guys do this for me? So we're looking at 0.25 times, oh, I'm not going to write anymore. I'll just let you guys calculate. Tell you what, I'll calculate too. Because I don't trust you. I'm sorry, I trust you. I was saying. I used to be fast at this. That O2 is just about irrelevant, isn't it? Yeah. I get 0.885. What'd you guys get? So about 0.89. All right. Now, let's see here. What should we expect the error is in this? I mean, how far apart is that from the true value? So the error, right, in Tn would be what? The absolute value of the integral from a to b, f of x dx, the real thing, minus Tn. This is the error, all right, the absolute error. And he actually gives us theorems. He gives us theorem in this section that put bounds on that, according to some things that you can calculate for the function. All right? So, oh, yeah, that page is missing now. Let's see here. I mean, I like this book. Don't get me wrong. I just don't like holding it. Oh man, it's not my best work. Oh well. Ah yes, error estimates. So here we go. This is something you could prove in perhaps a numerical methods class or something like that. The error in the nth trapezoid rule is equal to minus b over a cubed divided by 12n squared. F prime prime of C. In other words, there exists some such C in the interval from A to B to make it so. Now, we're not actually interested in, we're more interested in like putting a bound on the error, like saying we're that close, right? So like how you actually use this is then what this says, the straightforward implication of that theorem is there in the trapezoid rule is less than or equal to, okay, b minus a cubed over 12n squared m, where m is simply a bound on the second derivative. So, can we put a bound on the second derivative of the function in the example we just did? Can we put this error estimate to use and see if it's legit? Let's try it out. So, for our example, we have f of x equal to e to the minus x squared, right? So how do you put a bound on the second derivative of that? Mm-hmm. No. And in fact, I mean, I guess his error actually doesn't have the absolute value bars. So let's see here, let me fix it. I don't know. I mean, I'm interested in the positive error, so that, like, ignore minuses basically. All right, so how do we put a bound on this second derivative of this function? First of all, we better calculate the second derivative of the function, right? Oh man, I may regret this at this point. F prime of x is minus 2x e to the minus x squared. Yowzers. F prime prime of x is what? Ugh. Minus 2 e to the minus x squared, right? Plus 4x squared e to the minus x squared. There I did the product rule. So derivative of x is just 1, so that gives me minus 2 e to the minus x squared. And then the derivative of e to the minus x squared is again a minus 2x, but minus 2x times minus 2x is 4x squared. So I did the product rule and the chain rule. We can clean it up though. So what we have here is the second derivative of f is in fact 4x squared. Oh man, let me pull out a 2 here. That'd be better. So 2 times 2x squared minus 1 times the exponential of minus x squared. Now, that's actually pretty easy to analyze because the exponential is positive, right? Oh man, but I'm trying to put a bound on the second derivative, aren't I? I really need to go to the third derivative. F prime 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 of x equals to, I mean, you might do it a different way, but here's how I'm going to do it. So this is 4x e to the minus x squared plus 2 times 2x squared minus 1 times minus 2x. Man, I should have picked an easier example. E to the minus x squared. Oh well, what's done is done. All right, so let me see if I can write the third derivative over here. So what's the third derivative of f? Let's see if we can clean it up over here. Well, obviously there's an e to the minus x squared everywhere, right? So I'll pull that out. And what's left over is we've got 8x. We've got, what is that? 4x squared. 4x squared minus 2 times what, though? Times minus 2x, right? Be careful. Multiply that out, what do we get? Minus 8x cubed, right? Plus 4x. Plus 8x. Oh, this ain't bad. This is e to the minus x squared times 12x minus 8x cubed. Let me simplify this a little bit more. Can I pull out of something here? I think I can pull out a 4, right? So if I do that, this gives me 3 minus 2 x squared. What?
Wouldn't that second 8x be negative? Oh yeah, my bad.
I don't make mistakes. No, sorry. Sorry. Okay. Except the ones I make on purpose. Okay, it's not entirely truthful. Let's see here. So then, why am I after this? If I can show that f is increasing or decreasing, that gives me a simple way of bounding it, right? Like, notice, if we have f prime prime of x is greater than 0, right? For a less than or equal to x less than or equal to b, that tells me that f of a, it tells me that rather the second derivative of a is less than or equal to the second derivative. That tells me the second derivative is an increasing function. So the values of the second derivative at the endpoints bound the second derivative if the third derivative is positive. Now, I don't know if this third derivative is straight up positive on the integration region we're looking at. I'm not sure yet. I have to figure it out. So this is 4 e to the minus x squared x times what? 3 minus... Let me just get to the point here. When is this 0? Plus or minus 3 over root 2. I can draw a sign chart. And so I've got zeros on there, right? Where are my other critical points? Can you guys tell me, give me a decimal for this, if you don't mind? What's this approximately in terms of decimals? 1.22 plus or minus 1.22. Okay, so looks like this one over here doesn't really matter to us, but it looks like we're going to be, let's see here, how's this go? So if this is going to be, eventually that wins, right? So it's negative. The third function's decreasing out here, right? It flips to increasing here, right? And so forth. Well, it means negative over here, but whatever. So if you think about this, guys. So we're looking at the interval from 0 to 2, right? We need to find a bound on the second derivative. What's this tell us, basically? Let's think graphically for a second. It tells us the second derivative at 0, so I'm going to draw the second derivative here. Think about it. It starts somewhere, right? Here. Second derivative increases. All the way over to 1.22, right? And then what's it do? Decreases. Sound effects not necessary. 2, 0. So if you want to put a bound on the second derivative, all you got to do is look at this, this, and this. Right? Because that's its turning point. It can't turn around anywhere else. It's increasing, it's decreasing. So if you want to put a bound on the second derivative, all we got to do is calculate f prime prime of 0, f prime prime of 1.22, approximately, and then f prime prime of 2. Can you guys do those for me? Those will tell us what we can make the bound for the second derivative. So where's our formula for f prime prime? Over here, right? This guy. I'll do f of 0. I can do that one. Minus 2. Apparently my picture's a little bit off. right? -2 is where it starts, actually. Can you guys tell me what is the 1.22? You're making me do it, aren't you? All right. At this rate, I'm not even going to get the Simpsons rule. Let's see here. Oh man, where's my exponential on this thing? Come on. Exponential, what are we? 1.22? Squared though, right? And then that times 2 times parentheses 2.22 squared minus 1. I get 0.89. You get the 0.89? Okay. All right. So this is about 0.89. And how about 2?
0.25.
0.25.
26.
26? Okay, cool. So if you guys tell me then, you guys can, given all this work that we've done, what's the bound on the second derivative? Two, right. But, I mean, it's the absolute value we have to worry about. Okay, so what's this tell us then? If we believe this theorem about Simpson's, about the trapezoid rule, so we have that the error in the, let's see here, let's use the error in the fourth application of the trapezoid rule is supposed to be less than or equal to b minus a. My b is what? So I'm going to write it out here. B minus a cubed divided by 12n squared, right? The bound, what was our m? Yeah, okay. So for us, this is equal to, my b was what, 2? My a was 0. So we've got 2 cubed. 8 divided by 12 times 4. And my m happened to be 2. What? Oh, n is, you're right. I'm sorry, n is 4. You're right. That's 16, isn't it? Thank you. So what do we get? Oh, 1/12. So I get about 0.083 should be the, oh, I'm sorry, 0.083. We should be within 0.08 of the real answer. All right? You're like, okay, so how do you find out the real answer, right? The point of this is, the theorem is true. You don't need to know the real answer. Suppose you're working in an application and you just need to know what the integral is to a certain approximation, right? With this error approximation in hand, you can be confident that using Simpson's rule to a particular order is within, the truth to that precision. Now, we live in the age of computers, so we can do something else, right? Trapezoid, I'm sorry, I said Simpson's. Yeah, Simpson's rule is better. What's the error in Simpson's rule theorem? The error in Simpson's rule, order n, is less than or equal to, check this out. It happens to, oh, come on. Where'd you go? Fine, it's quicker. Sorry for those of you who are waiting for me to tear it out. You got to be careful. This is where I'll get confused. His different texts, you have different meanings for n here. So if you look at the error estimate for Simpson's rule in one book or another, you'll find different constants here. It's because the meaning of n is different in different books for Simpson's rule. And I would just tell you it's something you should look at carefully if you're going to actually apply it. But that's the error in Simpson's rule. Notice it converges to the truth even faster, right? Like n to the fourth versus n squared. I mean, that's getting the error, making the error smaller way, way faster. And the computational complexity of Simpson's rule versus trapezoid rule is pretty similar. The formula for Simpson's rule isn't much different than that. Simpson's rule is based on geometrically replacing the area. Instead of trapezoids, you replace it with quadratic interpolation of the data. So you like fit little parabolas to the thing and calculate the area under the parabolas, add them together. That gives you Simpson's rule. And but I want to show you how that bound works. So I'm going to focus on that here. That's why I spent most of my time this class showing you how to find a bound, because that's the part of the homework that you'll actually have trouble with. You have homework which asks you to find a bound, find an n which will make the error small enough given the rule. So basically, most of the challenge there is figuring out what's the form of the bound for the given function. I'm not actually going to ask you to calculate trapezoid or Simpson's rule on the test, because you guys are going to be busy doing integrals. And the last thing I want you to do is spend 20 minutes punching numbers into your calculate to find a number that you should be finding with a computer anyway. So, okay. So we're just trying to approximate what? Integral of exponential minus x squared, right? From x equals to 0 to x equals to 2. Am I right? I wonder if the internet's working in here today. We found 0.89. Allegedly, if we believe the theory, we should be. What's that? Oh, you used it. I didn't. Oh, stole my thunder.
You're on airplane. Yeah, you're on airplane.
That's not real. That's just there. It's my computer. That airplane's always there to make us worry. One of the many worthless features of Windows 10. Wow, this is it's really exciting. Come on, you stupid piece of junk. You can calculate. The cool thing is, you guys, if you just, man. Yeah, fine. Anyway, what did you get, Nathan, with your calculator? Assuming we can trust it. So you said that your calculator told you the integral from 0 to 2 of e to the minus x squared dx is equal to 0.88208. Okay, versus our T4, which gave us what? 0.089, right? So what's the difference? To quote a certain politician, what difference does it make? Sorry. Shouldn't speak ill of the dead. 0.89 minus 0.882, approximately, what do we get? Give or take? 0.01-ish? Am I right? What does this say? The error should be less than that, right? What does that tell you? What's the lesson we learned from this?
Do it on computer.
Ah, finally. Oh, look, it has a name. 1/2 square root of pi Earth. So what this is the name of the antiderivative. So all they've done really is just given a name to the antiderivative function of this, which exists, but it's not like built from sines and cosines and stuff.
Like Earth's error function?
Yeah. That is true. My point here, the moral of this story is we didn't keep enough decimals. If we kept 3 decimals, we might have been able to see it, but we only kept 2. So verification that the theorem really worked is in the gray area of it's in the round-off error of what we did over here, right? You always have to beware of machine epsilon. It's always lurking about, waiting to destroy your results. Do you guys know about machine epsilon? In every computer, you have a finite number of bits, right? So that means there's a biggest number you can represent, but on the other side of things, there's a smallest fraction you can represent. So that smallest number you can represent is machine epsilon. That is the finest precision that you can create on the computer. It's not like math. There is a smallest number. So what I was going to show you here, guys, is if you want to, if you're as you're doing the homework, if you do, you can do other stuff like sum I equals 1 to 100 of, let's see here, how about like 2I squared plus 3 times, I don't know, 1 over 100. So I mean, of course you can do this in Mathematica too, right? But I spent significantly less time doing this than using Mathematica personally. I spent a lot less time with licensing for Wolfram Alpha for some reason, but for example. All right. What would that be, by the way, just for kicks? So if you look at x naught equal to 0, right? And if we look at delta x equal to 1 over 100, right? So I'm thinking of maybe the integral from 0 to 1, right? So like my x sub I in this thing I'm thinking of here is actually equal to I. So what that summation is 2x squared plus 3 dx. That's the this is R100 for this integral. So this is, and so we get, what do we get? 6,770. What's the actual answer? Is that right? I think I set it up wrong. That's not right. Oh, I got the wrong idea. Sorry. Oh. No. I'm missing some numbers. I mean, x sub I is supposed to be equal to 0 plus I delta x, right? So if I want that to, well, anyway, forget it. We're out of time. Actually, we're not quite out of time. I just one parting comment with you. There is one simple kind of test question I can ask about this material, just to alert you to that. Just geometric question, basically. If you have a function which is increasing, which is a better approximation, left, right, left or right endpoint rule? What? Yeah. If it's decreasing, right. How about is Simpson's rule an overestimate or an underestimate based on concavity? Maybe trapezoid rule. If this is concave up, right, then Simpson's trapezoid rule will be a overestimate. Whereas if it's concave down, the trapezoid rule gives you a underestimate, right? And I think Simpson's rule is a little bit too subtle to ask about really geometrically. So anyway, that's pretty much all I wanted to tell you. I'm sorry I'm not giving you the deepest treatment of 8.7, but I think your efforts are better placed in all of the other sections. So thanks, guys. If you want to learn more about this, you should take Math 352 with Dr. Wang, numerical methods. There we get much deeper into these things.